we're going to turn our attention to coming up with an algebraic definition of a cross product. That means we are going to use components of our vector, and let's say we've got two vectors that live in R3. Is there a recipe for the cross product in terms of components? There is such a recipe. Key fact to coming up with this is that this vector A cross B is perpendicular to both A and B. And when vectors are perpendicular, that means we have to use the dot product. Let's say there's some third vector with these components, and I don't know what those components are. It's perpendicular to a vector A, and it's perpendicular to some vector B. And we want both of these things to be true. Now, just to try to illustrate this to you, let's say I give you a vector 1, 1, 1, and I give you a vector 1, 2, -1. If I were to go A dotted with C, I'd have C1 plus C2 plus C3, and I would like that to be 0. B dotted with C, that would give me C1 plus 2C2 minus C3 equals 0. This produces a system of two linear equations for C1, C2, and C3. What we will need to do is solve this system. I want you to realize that solving this system isn't just going to produce one answer. Here's A and here's B. We are interested in some third vector C that's perpendicular to both of them. The picture that I've drawn here is just one of the answers. I could draw a vector that's a little bit shorter or a little bit longer, or points down a little bit longer. There are infinitely many solutions. So if we go back to a general version of this, A is A1, A2, A3, B1, B2, and B3. And then we'll have this third vector, which represents the cross product, C1, C2, and C3. A dotted with C, A1, C1 plus A2, C2 plus A3, C3. Remember that the A and the B are known, C is the unknown. So we're going to encounter a lot of symbols here. So just make sure you're aware which are the ones we're supposed to know and which are the ones we are not supposed to know. Computing that second dot product gets me to here. And I'm going to label this as equation 1 and this as equation 2. Now, you've learned about solving systems at some point in your life. You can talk about things like elimination or substitution. I'm going to try to eliminate the letter C3 from both of these equations. So I'm going to multiply B3 times equation 1, and that's going to be the new equation 1. And I'm going to go negative A3 times equation 2, and that's going to become the new equation 2. Remember, you're allowed to multiply both sides of an equation by the same number, and it will still produce the same answers. A1, B3, that's the number in front of the C1. I'll have A2, B3, that's the number in front of the C2. And then I'll have A3, B3, that's the number in front of the C3. The other side here is going to give me a negative A3, B1 times C1. I'll have a negative A3, B3 times C2. And then I'll have a negative A3, B3 times C3. I'm now going to add this new equation 1 and 2 to produce the new equation 2. You can see the whole point of doing that step above was that those terms will cancel. So what this is going to do is give me an A1, B3 minus an A3, B1, groups of C1, A2, B3 minus an A3, B2, groups of C2, and that all has to be 0. We can call this alpha. We'll call it beta. I have two unknowns, C1 and C2, and I have one equation. When I have two variables in one equation, I have to have infinitely many solutions, just like I expect. So because there are infinitely many answers, I'm just going to choose one of them. If I choose C1 to be beta, and I choose C2 to be negative alpha, that means I'll get alpha beta plus beta times negative alpha, which will give me a 0. That means I know two of the components of my solution. I'll have C1 is beta, so that'll be A2 minus B3, subtract A3 times B2. C2 will be negative alpha, so that's negative A1 B3 minus A3 B1. C3, I don't know. I'm going to substitute these two things into the original equation 1. I have A1C1 plus A2C2 plus A3C3 is 0. I'm going to plug these things in. There is C1. There is C2. What I will get is A1 times A2B3 minus A3B2 plus A2 times negative A1B3 subtract A3B1 plus A3C3 is 0. This is the thing that I'm looking for. I'm going to do a little bit of algebra to clean this up. This term multiplied with that is the negative of this term multiplied with that, so that'll go away. I will have an A1 times negative A3B2. I will have a negative A2B3 times B1, and then I'll have an A3C3 is equal to 0. If I were to factor out common factor here of A3, negative A1B2, I apologize, this term up here should be a positive. So what I will have is negative A1B2 plus A2B1 plus C3 is 0. There are two answers to this equation. Either this term is 0 or this entire term is 0. Again, there are infinitely many answers possible. So we will take C3 is equal to A1B2 minus A2B1. And after this lot of work, this vector C, which we are really just representing as the cross product of A and B, first component, A2B3 minus A3B2, the negative of A1B3 minus A3B1, A1B2 minus A2B1. In the first component, there is no subscript for 1. All 2's and 3's, and they go in order, A2, B3, and then reverse order, A3, B2. In the second component, there is no 2 subscript. It goes in the same order, 1, 3, 3, 1. The only difference is that there's this negative sign here. And in the third component, guess what? There is no 3. A1B2 minus A2B1. This is one single vector. We will refer to this as the algebraic definition of the cross product. The last thing we need to sort out is its direction. If I were to use this formula and say I cross J, I already know that the answer has to be equal to K, but I want to see if my formula will produce this result. So 1, 0, 0. This is 0, 1, 0. The first component is supposed to be A2 times B3. So that's 0 times 0, subtract A3 times B2. That's 0 times 1. Then I'll get a negative A1 times B3. So that's 1 times 0, subtract A3 times B1. Well, that's 0 times 0. The third component will be A1 times B2. So that's 1 times 1, subtract A2 B1, which is 0 times 0. First entry is a 0. This second entry is a 0. This third entry is a 1. So at the end of the day, I produce 0, 0, 1, which is in fact k. The algebraic definition satisfies the right-hand rule, which is good. There's a simple way to remember the formula, and we are going to use something called a determinant. I'm going to write out that cross product formula again. A2B3 minus A3B2 negative A1B3 subtract A3B1 A1B2 minus A2B1. This stuff can be represented as a box. I'm going to put the A entries up top, A2, A3, B2, B3. And because this happens in the first component, I'm going to say that multiplied by the basis vector I. This quantity can be reproduced by taking this box and multiplying this diagonal entry and then subtracting that diagonal entry. So this is this 2 by 2 determinant. A determinant is a single number that you get from an array or a matrix of numbers. Now, the second term I'm going to have, it lives in the second component, so I'm going to put the negative sign with the j basis vector, and then just repeat this 2 by 2 determinant. A1, A3, B1, B3. This diagonal, subtract this diagonal. You're simply multiplying those two entries. And then the third term has a k in the front because it's in the third component. That number I get from putting in A1, A2, B1, B2, A1 times B2, subtract A2 times B1. So that's a very convenient way to get it. We are going to embed this in what's called a 3 by 3 determinant. If I give you an array that looks like this, I'm going to have x1, x2, x3, y1, y2, y3, z1, z2, and z3. When I compute a 3 by 3 determinant, I take the top number and I write it out front, and it's going to multiply a smaller 2 by 2 determinant. I'm going to take this column and cross it out, and this row and cross it out, and whatever is left is going to be the 2 by 2 determinant. y2, y3, z2, z3. Then I'm going to go to the next top entry, block out its column, block out its row. I'm going to put a subtraction, and then I'll have y1, y3, z1, z3. And then I'm going to go to the last entry, block out its column, block out its row. I'll have x3, and then the remaining sub-matrix here. y1, y2, z1, z2. Now, in our case, if I give you the cross product, the top row is going to be our 3 unit vectors, I, j, k. The second row will be the components of the first vector, and then the third row will be the components of that second vector. Now, just to try to illustrate this to you, here is an example. U is negative I plus 6k. That means I could write it as negative 1, 0, and 6. If I say V is 2i minus 5j minus 3k, that means it's going to be 2, negative 5, negative 3. U crossed with V. I'm going to build myself a 3 by 3 determinant. The top row will have the unit vectors I, j, and k. The second row will be the entries of the first vector, negative 1, 0, and 6. And then the entries of the next vector go here. The formula says take this first entry, block out this row, block out this column. So I'll have an I. And then the submatrix that's left will be 0, 6, negative 5, negative 3. I move on to the next entry and put a negative in front of it. That's the one key. Then I'll have a negative 1, 6, 2, and negative 3. And then I go to the last entry, block out its row and column, and then I will have k, negative 1, 0, 2, negative 5. If I now compute those 2 by 2 determinants, I'm going to take this first diagonal, 0 times 3 is 0, subtract 6 times negative 5. Then I'll get a negative j. I'll have negative 1 times negative 3 is 3, subtract 6 times 2 is 12. And then I'll get a k. Negative 1 times negative 5 is positive 5, subtract 2 times 0 is 0. So this is going to give me an I times a negative 30, a negative j times a negative 9, and a k times a 5. I'll get negative 30i plus 9j plus 5k. If I decided that I wanted to go v crossed with u, I'm going to build the same determinant. V is the second row. So 2, negative 5, negative 3, negative 1, 0, and 6. I'm going to compute this 3 by 3 determinant. I will mentally block off the top row, block off the first column. I'll have negative 5, negative 3, 0, and 6. Subtract j, block off the second column, first row. So 2, negative 3, negative 1, 6. And then k, block off the first row, third column, 2, negative 5, negative 1, 0. I, negative 30, subtract 0. Remember, multiply the diagonals. Negative j, multiply this diagonal, I'll get a 12. Subtract 3, plus k, 0, minus positive 5. So, negative 30i minus 9j minus 5k. And this is the opposite. Oops, I screwed up above. Here's where I screwed up. A negative times a negative gives me a positive. This has to be a positive. And now, shame on me, I get the right result. And this is, in fact, the negative of u cross v as expected. Now, there are other properties that are really important that we're going to come up with. I'm only going to show you one of them, but all of the others can be found using this determinant formulation. If I were to take CA crossed with B, so if I were to scale one of the vectors, this would give me a CA1, CA2, CA3, B1, B2, B3. Remember, I'm just multiplying one of the vectors. I'm stretching it. If I use my determinant formulation, I'll get CA2, CA3, B2, B3, subtract CA1, CA3, B1, B3, plus K times CA1, CA2, B1, B2. This is now going to lead to the following. Every single term is going to have that constant in there. Every single term in this 2 by 2 is going to have the constant in there. Every single term in this 2 by 2 determinant is going to have the constant in there. So what you can see is that you can factor out this constant. It gets to be put in front. All that I will have left is A2B3 minus A3B2, which is the first component. A1B3 minus A3B1, which is the second. And then a K in front of this, A1B2 minus A2B1. Well, you've seen that before. That's the cross product. So here's the nice property. If you scale one of the vectors, you are free to take that scalar out, or you could put the scalar on that second one. Now, others that I'm not going to prove, if you were to cross over a sum, it's the sum of the crosses. If you were to have a sum over a cross, it's going to be A cross C plus B cross C. Any vector crossed with the 0 is going to give you 0. Any vector crossed with itself is going to give you 0. And taking this vector ends up giving you that result.